טוב, אז שלום לכל המצטרפים, נקווה שיצטרפו אלינו עוד בהמשך. אני רק אגיד בתחילת דבריי שההרצאות שלנו מוקלטות ועולות אחר כך כקבצי יוטיוב לאתר של המוקד, אז שכולם ידעו שאנחנו מקליטים. אני מאוד שמחה לארח אצלנו בפורום מחבקי עצים של מוקד אקלים וקיימות סביבתית את פרופסור ניקולס וולדמן, קולגה וידיד מהחוג למדעים גיאו-ימיים מבית הספר למדעי הים. אני ניסיתי ככה לתרגם את מה שניקולס שלח לי מבחינת הביו שלו, אז תתקן אותי, ניסיתי לתרגם לעברית, למרות שההרצאה תהיה באנגלית, אז תקן אותי אם אני אומרת משהו לא מדויק. אז פרופסור ניקולס וולדמן הוא גיאולוג וסדימנטולוג, שלקח חלק במשלחות מחקר והפלגות מחקר רבות, בעל תואר שני בגיאוכימיה מהאוניברסיטה העברית בירושלים, הדוקטורט שלו בסדימנטולוגיה הוא מאוניברסיטת ג'נבה בשוויץ, פוסט דוקטורט באוניברסיטת ברגן בנורווגיה, שבו עסק בהידראטים של גז בצפון האוקיינוס האטלנטי, ולאחר מכן הגיע אלינו לאוניברסיטת חיפה, למחלקה למדעים גיאו-ימיים בבית הספר למדעי הים, שם הוא קיבל קביעות. בחיפה הוא הקים את הפטרולאב, שזאת המעבדה שנקראת Basin Analysis and Petrophysical Laboratory, שבה מבצעים כיום 15 חברי צוות את המחקרים שלהם, ומדובר בחברי סגל אקדמי, פוסט דוקטורנטים, דוקטורנטים, ואפילו סטודנטים לתואר שני. פרופסור וולדמן מדריך מחקרים שעוסקים ביוזמות מדעיות, שמתמקדות בהעמקת הידע לגבי יחסי הגומלין בין הדינמיקה האקלימית למערכת ההידרולוגית, וכמובן ההשלכות שלהן על הסביבה. נושאי המחקר נעים בין שינוי האקלים ושיחזור דינמית של מונסונים באזורים הטרופיים, וגם דוגמה נוספת, חקר יחסי הגומלין בין ה-Westerlies וה-Mid-Latitude Climate Systems. ניקולס השתתף בהפלגות מחקר רבות, כמו שאמרתי, בימים ובאגמים, כולל במלדיבים, בנורווגיה הארקטית, ובפרויקטים נוספים של ה-ICDP, בקניה, בים המלח ובאגן צ'אד, ובשנת 2013 הוא זכה בפרס קרי למצוינות מדעית מטעם קרן וולף. אז אחרי כל הדברים המרשימים האלה, אני אתן את הבמה לניקולס, אני מקווה שדייקתי במעבר מאנגלית לעברית. לבקשתו של ניקולס ההרצאה תינתן באנגלית, וזה בסדר גמור. כמדי מפגש, ההרצאה היא משהו כמו 40 דקות, ואחר כך יש לנו עוד רבע שעה לשאלות. אז תודה רבה, וניקולס, הבמה שלך.
תודה, ממש תודה, שלומית. האמת שאני יכול לתת אותה בעברית, אני פשוט כל כך רגיל לתת את ההרצאות שלי באנגלית, אז אוקיי. אבל בכל מקרה, אם יש שאלות, אני כאילו פתוח לגמרי לכל דבר. Okay, so thank you for coming today, and I'm going to talk about clues from the past and hydroclimate reconstruction from the Horn of Africa and Southern Arabia. Okay, and I will show you where actually the Horn of Africa, for those who doesn't know where it is. This is a talk that summarizes basically two PhD research, one of Ahmed and one of Pasha, who are co-authors of this talk. So basically, I will start with the fragile equilibrium between climate change and humans, and why I'm talking about the Horn of Africa and Southern Arabia. Okay, so recent studies show that the Middle East and North Africa, they are not only experiencing extreme high temperatures, but most importantly is that these extreme climate events last much longer than we used to be. I don't want to say normal, because normal, depending on the eye of the beholder, I will say, but they just last longer of the last measured in the historical record. And basically models predict that this pattern will strongly intensify in the coming decades. Now, this situation has major influence on food security, as this climate situation alters social and cultural practices like pastoralism, agriculture, and obviously it's causing political instability in the region. And but I also want to remind that this change in the extreme temperatures is also causing more pollutants in the air because of agriculture, because of human activities, but also because of the heat. You have more pollutants in the air, which eventually may lead to a situation in which could compromise habitability in some parts of the region. I won't say all the region, but some part of it could be very harsh to eventually live in the future. And I give you an example of the Horn of Africa. I will put my laser. Here you see the laser. So the Horn of Africa, that area of Africa, basically, which is Ethiopia, Somalia, Kenya, and Tanzania, that area in general. The example is given in March, November 2011 drought. There were more than 10 million people affected by these droughts, with estimations of more than 100,000 people dying during this period of time. And although we know that there were climate behind the massive amount of people dying, but there were many human factors with turn this crisis into a deadly emergency. And one of the obviously indications for the human factor, it's basically this map. It's this map. You can see a very strong variability between Kenya and Tanzania, for instance, or Kenya and Somalia. Like this limit between the countries, it doesn't mean that there is areas with stress or none food insecurity. It's just that governments have different ways or capabilities to handle the food insecurity issues. But in general, what he's saying that there was a very highly and acute food insecurity between Ethiopia and Kenya and Somalia. So there is a human factor. This is what I want to say. There were many indications, but in fact, there were many indications that the crisis in the Horn of Africa was coming already a year before with weather conditions into La Nina. Actually, we are now in a La Nina event, by the way. That's why it's endless winter that we are having with a lot of virus like the one I am having now. Anyway, so to give you a highlight of how the weather behaves in this part of the planet, basically it's a very peculiar area, the Horn of Africa, because you have basically two major rainy seasons. One is the March to May long rain season, known as the long rain season, and the other one is the October to December short rain season. And basically, it's one of these areas in the planet, one of the few in which you have two monsoon seasons. Why? Because the long rains, you have the southeasterly monsoons coming from the Indian Ocean in that direction. And October, December, you have the northeasterly monsoon coming in that direction. So both of them provide with rain, with humidity, but one is longer time and the other one is shorter time. So that's why it's the long rains and short rains. Now, what happened in 2011? That already since 1980s, actually, this is like 30 years before 2011, the Horn of Africa started to experience persistent decline in rainfall during the long rain. They knew it. It didn't come out of the blue one day after the other. They knew that there is a decline in rainfall. Now, this is a major issue for the Horn of Africa, in which most of these countries rely on agriculture for human sustain. Now, once you are switching off the major input of water into the region, which is the long rain, so you are contributing to a disaster in the agriculture and economy. Now, it is it is a little bit unclear whether this decline was caused by internal multi-decadal variability, which is associated to ENSO, El Niño event, or anthropogenic driven warming in the Indo-Pacific region. One way or the other, what do we know is that change in precipitation in the area is associated here, the Horn of Africa, is associated with the conditions which are prevailing in the ocean. In this case, what happened during the year before March, November 2011, that there was an increase, a substantial decrease in temperatures in that area of the Indian Ocean. Once you are decreasing the temperature of the water here, you are basically decreasing or shutting down completely the water that is going to come into the land by rain. And this is related to the water circulation, which is over the Pacific and Indian Ocean, providing with influencing that part of the Indian Ocean, okay? So basically, that was what happened a year before, and it was decreasing during the last 30 years before 2011. If I move to the Southern Arabia, I give you another example from Yemen in 2015. In this case, there was, since ever kind of, but there was a political instability and wars that ravaged Yemen into and scattered the country into sections, with obviously had caused a very high burden on resources management in the country. In fact, this has turned the society that is based mostly in pastoralism and agriculture to be even more highly susceptible into minor change in water susceptibility, in water availability, sorry. So what happened is that there were extreme droughts occurring during December 2014, again, a year before 2015, that developed into an acute food security situation in many parts of Yemen, as you can see here in the map. By the way, this doesn't mean that there was not acute situation here. It's just you basically have less people living there, okay? So the share of the wealth is better share about the population, in which the situation is more complex when you have more population, right? So what happened, again, another example, 5 years later, February 2020, you have the contrast, the other situation in which you have extreme rain during the short rain period in the Horn of Africa. And this is the connection between the Horn of Africa and Yemen. What happened is this extreme rain caused a large amount of water into the area. This water eventually created much more flooding in the region, lakes, inundation, and so over, which eventually, several months later, caused an infestation of locusts in the region that moved into Yemen and moved northwards into the Saudi Arabia Peninsula and actually arrived into Israel that year. I remember in the news, they saw locusts in Tel Aviv, as much as I remember. So it was a massive, but it was much massive than normal. Again, I don't want to say normal because normal is it's a change normality, but it was much massive and extreme that the years before that, and it caused a disaster for these countries, which again they rely heavily on pastoralism and agriculture, and caused them extreme acute food insecurity. So again, we're talking about extremes, and in a relatively short period of time. So what we need to know actually is to know how these extremes behave, or if actually there are extremes when we are talking in a long time period. And this is what I'm doing. I'm a paleoclimatologist. So I check sediments in the long term in order to understand the pattern, in order to provide a data for the present situation, and eventually a modelist will take that information into a model for predicting the future. So in this case, this is a paper by Jessica Tierney from 2015 from course from a course in the Gulf of Aden, which is basically in between Yemen and in the Horn of Africa, and providing a much longer record that goes over 2,000 years. And what we can see here is that indeed, the last 400 years are typified by the increase in dryness, okay? Steep increase in dryness. We did have dryness in the past, but it was not a steep and short time and the extremes so high as now. And we did have period with less dryness in the past. Okay. Now, what we need to know, and however, we need to know how we understand this record from in the terrestrial environment, in the areas in which we humans will live, and how this is translated into the continents, basically. So that's why I'm taking two examples, one from Lake Chala, which is in Kenya, Tanzania, exactly in the border, and the other one from Gaya al-Bawazir, which is in Yemen, southern Yemen. These two sites over there. So this is Lake Chala. This is the way it looked like. It's a beautiful, fantastic, astonishing lake, which is located in the Kilimanjaro area. It's a very small lake, actually, only 4.2 kilometers square with a water depth of 94 meters. Most of the water comes by local rainfall and 80% by inflow, subsurface inflow from Mount Kilimanjaro. It's located at 800, if I'm not wrong, 800-meter high. It's basically, it's a volcanic crater. It's a volcanic cone that belongs to the massive Kilimanjaro volcano that exploded, and then the lake water basically filled up that basin. Okay. So why this lake? I mean, we have many lakes. There is Naivasha, Victoria, Edward, many famous and with a lot of PR, right? Why Chala? Nobody heard about Chala. When? Well, I explain you why. Because this lake, the studies again, Jessica Tierney, in this case, 2013, she shows that most of the water arriving to this lake, like 99%, comes from the Indian Ocean. Not like Lake Victoria or Lake Edward. Lake Edward is mostly water coming from the Atlantic Ocean. Victoria is half-half, and this is a mix, but this is like a pure, pristine record of the Indian Ocean, which this is what we need when we are talking about the Indian Ocean monsoon system, right? Because there is the African monsoon system. What you can see the colors here is the brown area will be the areas more influenced by the African monsoon system, while the blues are the Indian Ocean monsoon system areas. In between, there is the Congo air boundary, which divides these two areas, okay? And goes until Ethiopia. Ethiopia is a little bit of mix of both. And then Yemen is influenced by the Indian Ocean monsoon system. So that's why Lake Chala. Already in the early 2000s, seismics, geophysical prospecting of the lake was taking place. And what you see here is basically the volcanic crater, right? Which was, you don't see the volcano, you see the sediments inside the volcano, right? With all these seismic phases, which basically are showing the layering of the lake. Very beautiful cone, very well layered, pristine, and with several horizons that they were marked there. Now, what happened in 2016, a long, deep Chala core of the ICDP. The ICDP is the International Continental Scientific Research Drilling Program, which is based in Potsdam in Germany. And it's an association of countries from the planet that basically they have the facility. We pay the money. We are members of this association, and we have the possibility to participate in international drilling programs or to actually make a drilling program. So there was one here in Israel in 2010 in the Dead Sea, and this one in 2016 in Lake Chala in Kenya. And I was lucky to be a member of this project and be there in the lake for almost 2 months. So potentially this is what we got. We got, sorry, one site with several drilling. What you see here, for instance, site 1A was between 0 and 100 and something, then another one, then we drill with no coring just to obtain the rest, and then so on. Eventually you get this, which this is the summary of everything together with 100% of recovery for the 150,000 meter depth, sorry, and the rest, it's a very well high recovery rate of 96%. This is extremely excellent, because you always get problems or lack or sediments or whatsoever, and having 95 or 96% of recovery, it's like, wow. Okay, and here, this is the information and the countries that participate in this project. And I show you here a small video of how it looked like to drill and core. With the music, I chose the music. So this is the barge, which is from United States with South African drilling team and international scientific team. You can see the Kilimanjaro in the background. The drilling happens 24 hours a day with 12 hours change. I was leader of the night shift. So it's 8 in the night until 8 in the morning. And to tell you, to be honest, it's much better to be in the night because you don't get burned by the sun, but you get a lot of mosquitoes. So what you can see here is one after the other, the barrel. Each barrel is like 6 meters, goes down and go down and go down. Well, you don't see that they don't go down because actually exactly when we took the picture, the movie, we had problems. Like always I say, every time that you go to the field, you may have problems, you may have an issue, you may have something. Now it goes, you see? Now it goes down, 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 and every time, basically you have something like 6,000 years that you are drilling. And here comes the monsoon with the rain and the mosquitoes, and a lot of mosquitoes. And this goes for a month that you basically work 8 to 8 and try to maximize the work, because every day, every hour costs money and a lot of money. This is a project with several millions of dollars. So yeah, you need to maximize it. So about the results of this project, in general, I will show you 3 parts. One, which is the seismic stratigraphy, which is the geophysics, then the lithostratigraphy, which is the sediments, and then a depth matching between one to the other. The geophysics and the sediments, they need to talk together. Otherwise, they are like 2 satellites and we don't know what they need. So these are the geophysics. This is the work of my PhD student who finished basically this year. And what you can see in summary, I know that you may not have a geophysical background, and so I will summarize very quickly. When you have this kind of pattern, you try to imply, this is what you see here is the sedimentary facies, which respond to what kind of densities you have in the sediment, like a sonar, like ultrasound in the body that we do. And you see the densities contrast. What you can see here is interpretation of all these densities and cleaning and all that. We can get several patterns, and I highlight mainly 2 patterns, one of them of the layers of the architecture. You have here very nicely parallel stacked architecture of layers, and another one which is it's parallel, but once we go to the south, you see that everything pinch out into the area, into the corner. So what the difference, this will be ponding, draping kind of sedimentation, and this is ponding kind of sedimentation. This is a high lake level, and this is a low lake level. That's basics for geophysics, okay? So basically, and then we have a mixed starting between ponding and draping, okay? So basically, once we take that initial analysis into all the structure, there is several seismic units and so on. All that is highly described by my student. But in general, what we were able to, and what, again, and another thing that we see also is a lot of these yellowish structures, that they are basically sediment displacement units, or mass transport deposits, or mass wasting events. There are many names to that thing, but basically sediments coming down from the upper part of the lake or the basin into the lower part. Very easy. And they were mapped. So eventually, the interpretation of all the seismic lines and everything, we can define several stages in evolution of this lake. One stage of initial filling up of the volcanic cone, a very rapid increase in lake level, a decrease, and then an increase in stable situation. So you have several stages of increase, decrease, increase, and decrease, and so on, which basically can be translated into more water or less water, more rain or less rain, or eventually what we are pointing out, the influence of the Indian Ocean monsoon system, because we know this lake was always influenced by that. Then we come back to the lithofacies analysis. Now, it was impressive, I'm telling you. I mean, pristine, highly laminated, millimeter by millimeter of beautiful mud. But basically, this is not really mud. This is purely diatoms. So basically, you have a whitish millimeter scale layer of datum, and then more another kind of datum. You don't have, basically, it's not like mud, like you go to the Dead Sea and you put your body in mud. This is not mud. This is a sponge of datums. I cleaned that for 2 months, cleaning the sediments, and it was totally different from anything I saw in my life. So it's purely like 90% datums. Datums, a microfossil living in the lake. Sometimes, obviously, you have clay. You have more clayey material when you go down. But in general, mostly it was datums, different kind of lamination, highly laminated, less dummy, highly laminated, more blurry, wavy laminated. And these are basically the start for defining what do you have. You have facies 1, facies 2, facies 3, and so on. So you define. You cannot define 100, you get lost, and you cannot define 2. You need to be some kind of normal with it. And the definition of the facies, eventually, these two, slumps, turbidites, and tephra, these are different. Slumps is when you have slumps, right, coming from the side. Turbidite and slump is kind of the same thing. I don't want to get into too much into that. And tephra is volcanic explosions, basically. So you have the volcanic ash, okay, that unit with it. So we consider them a little bit differently. But eventually, when you are dividing into facies 1, 2, 3, or whatsoever, you can generate a clean code for your record. Instead of having a long picture, which is beautiful, you can transform it into facies 1, 2, 3, 4, whatsoever, which this is what my student did. And once you have that, you can correlate your information with the seismics, okay? Now, you will see that it doesn't match exactly the depths, because this is in time, because it's a sonar, right? And this is in meter. It's not in time, it's in actual meter. And I will talk a little bit later, okay? So what you see here is a translation from the lithology, from the sediments into the seismics, into the understanding of the high lake level, low lake level, which they pretty much match very well. And then a generation of a lake level curve is not absolute. I mean, we don't know exactly if it was 89.6 meters. We know it was high or low or medium, but we don't know exactly the altitude because we don't have that marker. But what is interesting with all these MWDs, the slumping material, right, that I was saying. So it is interesting that you have much more slumping wherever the lake level is high than wherever is the lake level is low. And basically, this is because you have or a steep increase in the lake level, and then that instability caused the sediment to slump, or rather you have sediments forming in the shoulder that can slump. You need that shoulder to slump. Otherwise, if you don't have the shoulder, they will not slump. But anyway, this is a very nice and interesting correlation between the instability of the slope and the lake level, which this is, you can transform that information to any lake in the planet or the ocean. You can transform it to the Dead Sea. You can transform that information into the Mediterranean here and what so on. What could happen if the sea level will increase? You will have more slumping or not? This is a question. So, I mean, that information can be translated anywhere in the planet. And why I was saying before, these lines that are not exactly horizontal, exactly because of that. This is the downhole logging. This is an instrument that you put inside the hole once you take out the sediment. And this is the sediment itself, the logging on the core, on the sediment. Okay, and eventually the comparison between two, I don't show that picture here, but eventually this data and this data are compared together and generate a composite record of the lake, okay? But it's like you fix one with the other, right? Okay, we cannot talk anything if we don't have an age, right? So when you're dealing with long core records, we start to have a problem. As you know, radiocarbon dating technique will go to 50,000, and over there you also have some kind of a problem. But when you go deeper in time, you need other techniques, and you may have other options for you to use depending on the systematics on the lake, lithology, biota, name it. In this case, what it was done, it's exactly those tephras that I showed before, these ash layers of that we find in the sediments. So each one of those, it's basically a tephra, an ash layer from a volcano. Now it can be a volcano which is somewhere in the rift, the East African rift, you see, all these highlighted here, or it can be a very long distance volcano. It's very interesting what you can see here. This is a recent paper, actually, it was a couple of months ago. So what you can see here is the distance. This is 7,000 kilometers and beyond. So most of the volcanoes, they are 100 kilometers less, somewhere in that area. But some of them, they are much longer in distance. And what I can highlight here is where it is this one. YTT. YTT is Toba. The Toba volcano, it's in Indonesia, and it was a huge volcano event, which basically changed the climate of the planet for several hundreds of years, if not more. And that volcano even changed here in Israel. But what was impressive that they actually found the tephra. It's a micro tephra, it's a crypto tephra. You don't see it by eye. You need to actually sample it and put it under the microscope, and you will see the shards, the silica shards. But it was impressive that we found it, basically. And it's coming from the Indian Ocean all the way to Africa. And it's an excellent horizon to put an age, because we know exactly when it happens. We are extremely happy that we have also one in the bottom, because we can anchor the bottom as well. Okay, otherwise you get blurry, the bottom, the age. So anyway, we get the tephra chronology, okay? And then when we compare the tephra chronology with the seismic, this is a seismic-based age chronology, we can generate an age depth model, basically, in which sedimentation rates vary a little bit according to a high lake level, low lake level, and eventually the outcome will be generating a high lake level, low lake level curve. Eventually all this information can be translated into understanding when you have more or less water. There is a highlight here, which happens here, 80 meters water depth, which is somewhere like 100 and something thousand, 120,000 years ago. And this is what is called stage 3 in this lake, but this is what is called the mega African drought. And this mega African drought is known from other side in Africa. And it was an extreme period of drought in sub-Saharan, the Sahel and Sahara area, and also other parts in the region, which may provide an insight to the present situation of drying, okay? So some summary about Lake Chala. So we have a complete record of the lake evolution system since it was burned, so since the beginning, which an estimation of actually 2050, actually 2060 mostly. We fixed it. This will be the oldest point of oldest depths of Lake Chala. And as I say, purely pristine, finely laminated diatomites with a little bit of clay all over the way. And it gives an excellent record of the climate for the last 250,000 years. Now I move to Yemen. Obviously, I didn't went to Yemen, guys. No, with the situation and the previous situation, even that I have a double nationality, I won't go there to take this core. Luckily, the core was taken by our colleagues in the United States. It was like 20 years ago. And this is in the site of Gayar Bawazir in southern Yemen, which is there. Okay, this is the area. And if we highlight the area, this will be the drainage pattern of that site. This is the little area. And when we highlight even more, so what you see here, this is the lake, which doesn't exist anymore. And the small area of drainage of that area. What we are saying, we are in an area of carbonate rocks and like limestone, like here in Haifa, with much less rain, obviously, and with karstic holes. What you see here is a karst hole. Okay, so it's interesting that there is karst in that part of the planet. What you can see here is the the weather pattern in that area. Sorry. With the more increasing precipitation actually happening during those months, which is March, April, May, and a little bit of precipitation also in June, July. This is related to the monsoon system. Okay. So some results of this core. We have accessibility for this core, which is sitting in my lab, and more than 3 meters of sediments, very well layered. It's not laminated as the one in Kenya, but it's very well layered with a lot of different sedimentary phases. You can see the color here, changing from something more thick. It's a thick 30 centimeter unit, much more grayish, maybe greenish a little bit, and then changing into whitish material, more dark, more whitish, yellowish, and so on. A lot of gypsum, by the way. So it's a total different system than the one in Kenya, a different environment, different climate, a little bit, and so on. But still, what you can see is a very nice record, complete record. In this case, showing here again several sedimentary phases, sandy silt, clayey silt, and silty sand. Again, you will define the sediment according to the place, and it will vary obviously according to the place. And the data of the inorganic geochemistry, you can see here the major components, for instance, calcium against iron, titanium, and aluminum, which basically is the element that represent whatever is formed within the lake and the elements that come from outside the lake. I mean, there is a meaning why we ratio one element to the other, right? And other elements. This element ratio allows us to actually divide the record into 3 different lithological units, units 1, 2, 3, that you can see here. And that the behavior, the sediments a little bit look different, and also the behavior of the geochemistry looks different. And what I want to show here is a little bit of that. And again, here, this you can see.
נשארו לנו עוד 5 דקות, אז...
5 דקות? Oh, Jesus. Okay, so I will push forward.
תודה רבה, תודה.
No problem. Here you can see the magnetic susceptibility, which is the magnetic signal of the sediments, and the total organic carbon. I push forward, sorry. And the grain size. So we analyze the physical properties, the chemical properties, and also the biological properties. I push forward, and we have an age that is based purely on radiocarbon, and very nice age depth model. And you can see here again going back to 1,000 and something 1,000 years ago. So when you take all these physical and chemical properties together, we define here periods of high lake level, more impact of water and less impact of water, which we correlate to the medieval climate anomaly and the Little Ice Age. Medieval climate anomaly, basically you have more water, but as a flash floods, okay? Like in the Little Ice Age, you have more dryness and less water, okay? And what you can see here above, this will be the human influence. All of the data actually show a lot of anthropogenic impact already starting 100 and something years ago. Okay, that's why everything is blurry over there. So I run forward. What you can see here is that each one of these records behave a little bit different during these periods, implying more or less water into the system, more or less influence of the monsoon system. And then when we correlate that into other areas like the marine, this is Arabian Sea, this is Kenya, this is also Tanzania, we see similar patterns. So it's confirming that our interpretation actually behaves like in the region, like in the Horn of Africa and the Gulf of Aden, we have the same pattern of increased rain or decreased rain during the Little Ice Age. This is the first Little Ice record in all the Southern Arabian Peninsula. So this is a very interesting work. Also, this is by Pars Shah in 2021. We continued the work and we wanted to know the impact on the ecosystem. So we checked the biological markers, in this case, the lipid biomarkers or NLCan. And here again, what you see, a summary, because I'm pushed to end. So what you see here is again, more terrestrial aquatic plants in the lower part of the lake, more terrestrial in the central part during the Little Ice Age. And also again here, you have the influence of humans and anthropogenic impact. But you can see very nice the variability between terrestrial and aquatic plants in the lake. And we have also chironomids and we have ostracods, but I don't show because we don't have time. So, summary of Yemen. This study provides comprehensive picture at a very high resolution, extremely very high resolution, of the intensity of the monsoon during the late Holocene and the spatial coverage of the area. This is the first lake ever studied in the Arabian Peninsula, if you don't consider Israel part. The evolution of this paleo lake has been controlled by climate factor. This is what you see. We see the medieval climate anomaly and the Little Ice Age. A medieval climate anomaly here with decreased salinity, increase in aquatic and more rain, more fluvial input, more nutrient rich, and Little Ice Age, decrease in the lake, more dissolved oxygen isotope, oxygen dissolved in the water, and increased salinity. Okay. And all that is related to the solar variability invoked by zonal shift in the ITCZ, which is the monsoon variability. Summary of everything, when you compare all the stuff, all this Yemen and Kenya, the Kenya provides you a long information of the last 260,000 years ago of long and short rains, right? While Yemen provides you a very high resolution impact of the last 2,000 years. And again, both of them, they are both records are related to the orbital forcing and to the Indian Ocean monsoon system. In the case of the Yemen, we see the Little Ice Age and the medieval climate anomaly. In the case of Lake Chala, we go far and we see the mega droughts of 130,000 years ago. Actually, we see something similar in Israel, in the Dead Sea record, very obviously. But eventually, both records provide important insight into understanding how climate impacts the hydrology and modern societies in the region. And as I say, I am not alone in this project. We have two students that they finish, both of them, one of them already finished, one of them is finishing right now. Both these two projects and collaborations in Belgium, Germany, United States, Kenya, Tanzania, UK, and probably I forgot, but this is not alone. I'm not alone. Thank you very much. Did I manage? In time.
תודה רבה לניקולס,
תודה לך, רבה לך.
גם על ההרצאה באמת מרתקת, שפתחה ככה עולמות מחקריים חדשים, וגם על העמידה בזמנים. שאלות מהקהל?
אין שאלות?
אני רואה שאין שאלות.
חשבתי שתפוצצו בשאלות. אם הכל היה ברור באנגלית.
כן, כן. הזדמנות אחרונה לשאלות? אוקיי, אז ניקולס, שוב תודה רבה.
תודה שלומית.
ההרצאה גם תעלה כסרטון יוטיוב אחר כך לאתר של המוקד. תודה לכולם על ההשתתפות, ואני אישית למדתי המון. ושיהיה לנו שבוע שקט וטוב. תודה רבה.
תודה על ההזמנה שלו.
ביי ביי.
תודה לכם.
תודה.
תודה.